Hi, welcome to the Calculus 3 assignment practice series. And we are in the unit vector calculus. And this is our assignment number 10. And we are going to work on some problems related to the Stokes theories here. Okay, so now let's go ahead and take a look and what type of the problems we have on this assignment with regarding to the Stokes theories here. Okay, I'm going to go to our assignment sheets here. So this is assignment number 10 worksheets here. All right, so the one I highlighted in the red, that's the problem we're going to work here. Okay, so the first ones here, they tells a hemisphere H and the portion P of a paraboloid are shown here. So I have two surfaces here. Suppose F is a vector field on R3, then whose components have a continuous partial derivative. So now we say why, the surface integration of the curl of F is equal to the surface integration of the curl of the F for the P's here. Because, in here, based on the Stokes series, right? So we said the Stokes series, the surface integration is equal to the curve bounded this surface, right? So the curves here is, if you take a look, let me see here, I can highlight that. So the curves here, if you see, is like the red, is like a kind of the circles, right? So that's why, and this is the same, when they intersect the XY plane. So it's the circle. And then you notice it, they both have what? They both have the same circles here, right? So the circles here, so we said both, the reason why is both the H and the P, these surfaces are what? Are bounded by, bounded by a simple closed smooth curve, simple closed smooth curve, right? And what is this curve? It's a circles, right? So this is x squared plus y squared equal to 4 when z equal to 0. And so C is a bounded curve. Then based on the, so this is, we call it, this is the curve C is here. So based on the Stokes series, so what is this going to equal to? This is going to equal to the C, the curves, right? So will be the F what? F and the D, the R's, right? Okay, so the same, this ones here is the same. You integrate the line integral of the vector field and the dR's, right? Okay, so because the curves are the same, so that's why these two surface integrations are the same here. So that's why it tells us, doesn't matter what the surface, like if this surface is bounded by the same curve, then the integration of the curl for the F will be the same based on the Stokes series here. All right, so now let's take a look at the problem number 3 here. Okay, so the problem number 3 is just, so this is my vector functions, right? Y, E, Y, Z, X cosine Y, and the S is a part of the paraboloid, so it's X squared plus Y squared plus Z squared equal to 16, and the Y is greater than equal to 0, and oriented in the direction of the positive, in the positive y-axis here. Okay, so first, let me try to see, I can do a good graph here. Okay, so this should be sphere, sorry, so it's not a paraboloid, so it should be spheres, right? Okay, so now in here, let's see here, this is my X, this is my Y, and this is my Z here, right? So here. So basically it's a half of the sphere, and I'm circling around the y positive y-axis is here. So let me see, I can graph this. So this one, so it will be something like the half of the sphere. So it's here. Okay, and then, oh, it's not bad. I think I did a pretty good job to graph this. All right, and then it said because I'm rotating along the positive y-axis, so basically, so this is the rotations I have, right? So this rotation, this is the sense, and it will be the counterclockwise rotation, so it's a positive orientation. So then this one is basically, this half of the sphere basically is sitting on the plane z and x, correct? All right, okay, so now in order to do that now, so let's take a look, how do I do the, this is part of the integration. So let's try to take a look, how can I do the, find the surface integrations, all right, for the curl f. Okay, so in order to do that, so I know because this curve here, right? So this is the one bounded by this curve. This is the circle sitting on the xz, right? So it's go this way, go this way, go this way, go this way. So here, okay, all right. So now I know here. Let's write down here. So the boundary curve, right? So the boundary curve C is what? It's a circle, right? And this circle is what? Is x squared plus z squared equal to what? It equal to 16, y equal to 0, right? Okay, so that means where is this one touch the xz planes here, okay? And now we'll be able to see here. So let's try to find the parameterizations here. So the R, okay? So let's see the RT is here, okay? Well, let's do this one here. Let's set, maybe let's do the x equal to the xt. So here x equal to x function of the t. So we know since the path is a circle, so very naturally we will do is what is sine cosines, right? Okay, so my t obviously is going to from the 0 to 2 pi here. Okay, be careful here because in here, right? So if you see here, we are rotating these directions, right? So my xt's here will be what? So this one's here, my xt's here will be the 4 cosine negative t, right? Because when you're rotating that, so you are rotating to the xz, you're rotating this direction, so it's negative t. And then because cosine is an even function, so this is a cosine t here, okay? Then it's the same way for the y's here is a function of the t's, right? So what is the function of the t's here? So y is the 4, the sine, the same way because the angle rotating the negative, the negative directions there. So this will be the negative 4 sine what? 4 sine t's here, all right? And so the, okay, I'm sorry. So the y is 0. So what I'm thinking, y is 0 here. So this is what? I'm sorry here. So this is our z's here. Okay, so it's zt's here. It's negative for sine. So it's negative for sine. So the sine t. So now I know my RTs right now is 3-dimensional, right? So the first one is 4 cosine t. Y is equal to 0, and my k is what? Is negative 4 sine t, that's right. So after you find your parametric equation, so what do we do next? We are taking the derivatives for that, right? So it's RT's here, R prime t. So this will be negative 4 sine t, and the 0, and then this is negative 4 sine t, correct? Oh, so cosine t, sine t, cosine t is here. All right, so here, this is cosine t is here. Now I'm putting the f functions here, right? Okay, so now I need to put this parametrization to my f functions here, so I can change everything to t. Okay, so the f function is ey, y is equal to 0, right? So it's e0. What is z here? Z is negative 4 sine t, correct? All right, good. So this is my I component. And then x cosine y, x is what? Is 4 cosine t. What is the cosine y? Okay, so cosine zeros, right? So this is my j components. And then plus the last one is xz sine y. xz, x is what? Is 4 cosine t. And xz, z is negative 4 sine t. Okay, now here is what? Sine y, so sine 0. Okay, so now I know this term, because sine 0 is equal to 0, this term going to be 0. And what is the cosine 0 here? Cosine 0 is 1, right? So I know after then my functions here, it will be in my field, I can change this to a one variable function. So it's negative 4 sine t. So this is still have I components, and this is a 4 cosine t j component. So what happens to my k components is 0 to the k's here. All right. So now we know by the Stokes theorem, I can just dot product, right? So the in here, so now I can say the surface integration of the curl of the f, right, will be equal to the line integral of the f dot dr, right? Okay, so the f dot dr, so this is f, right? So let's say the f dot dr, r prime is here, right? So f dot dr is here. So r prime, let's put the r prime here. So f dot the r prime here, right? Okay, so this is f dot the r prime. F is here, right? So f is this one, and the dot product this one. So what I have here, f dot r prime, I have, this is an, oh, pretty good. So it's what? I have 16 what? Sine square. Okay, so let's simplify that. It's 16 sine squares here. Okay, so now I can rewrite this one. So what is the t? T is from 0 to 2 pi, and 16 sine square t dt, right? So this is a very typical calculus 2 integration, the trig integration, and you can do that by using the double angle. So right, we talk about is using the double angle. So this will be the 16. After I simplify that, is 1/2 t minus 1/4 sine 2t. All right, so then my limit is 0 to 2 pi. So here my answer is 16 pi for this problem here. So the key things here is, if you cannot visualize this, right? So you might want to do a demo by yourself and put the XYZ layer, and then you try to rotate in that. So the key things here is when you parameterize it, right? So this is negative t's here, because the angle go to the negative directions here. All right, so now after that, it will just be the simple, like what the problem we did before for the line integrals here. Okay, so the next one I'm going to do is the number 5 here, right? Okay, so the number 5, we're telling you, see here, they said f of x, y, z here, right? So this is my field, consists of the top and the 4 sides, not the bottom, okay? Not at the bottom of the cube here. So that's why I have a surface here. with vertices is plus minus 1. So the four corners will be like the plus minus 1. So I hope I can do a good graph here. I probably will have a hard time to do that. All right. So basically, you're going to have right. So basically, so in here, I hope that you can see here, you can have basically you have like a square box, right? So basically you have a square box, and then this one's here is going to, what is the, the bottom surface here. So if, I don't know, you can visualize or not. So the bottom surface is here going to sit in the where, right? So I know that this bottom surface is here, right? So it's the square is going to sit on the z equal to the -1. And because I'm going to use the Stokes theorem, that's why I'm only care about the top ones here. So this is my top one and the four side, right? So the four side, and not to worry about the bottom one. So in here, that's why I said the bottom one, I just want to show you. So you know where the bottom one sit, right? And now we are using the Stokes, right? So I'm only care about the top one and the four side, right? So that is surfaces here. Okay, so now let's take a look. So here, right? So this one's here, we have some, the interesting things we talk about in our lecture, in our lectures here. Okay, so the first one here, I want to find the surface integrations, right? Okay, so let's take a look here, right? So the curl, let's take a look at curl F, see here. So the curl F here, so this is the F. I assume everybody now know how to find the curls of the F. So this one will be, I already did here. So x squared z is the I plus xy and minus 2xyz, right? This is the J. And then plus the y minus xz to the k. All right. All right. Okay. So now, so this is to the case here. So this is, you just need to use our definition we did many times, like ij case here. And then you have rho x, rho y, rho z's, right? Then you have PQRs here, right? So that's what you can find the curl. So we find the curl here, right? So this is we find it, I assume you know how to find it, okay? So now we know, all right? So here, okay? So the curl, so I'm doing the surface integrations, right? So here, so this is the S, and then the curl to the surface integration. And so remember the surface integration, you need to parameterize your surfaces here, right? And now, you parameterize your surfaces here, but in here, we said that when you parameterize your surfaces, you really, it's kind of like, so, you really is kind of like find we said the RUV, right? So RU cross RVs, right? So it will give you what? It will give you, this one here will give you a normal vector, okay? This will give you a normal vector. So like in here, so like if this yellow one, I call it S1, then the bottom one, I call it S2 here, okay? So be careful. If I want to find the surface integration of this yellow one, so how many surfaces I need to do? I need to do what? I need to do, basically I need to do 5 different surface integrations, right? But based on the Stokes theorem, so if you take a look, this is the bottom square, right? So this is the bottom square here, right? So this is a boundary. So the bottom square really, so if, let me put this one's out, maybe it will be easier to see, okay? So here, okay, so then here, right? So then if you take a look here, right? So here, this one's here, this is the, this is the closed curves, right? They bounded by both this bottom one, right? So both this bottom one and the surface, the 5 surfaces on the top and the 5 side, right? So like then you say, hey, I want to find the surface integration of S1s here, right? So really, this ones here is the same, the surface integration of S2, correct? The reason why is why? Because by the Stokes theorem, just like from the example, the problem number 1, we say if they are bounded by the same closed curve, then that doesn't matter, right? Then the surface integration will be equal. So now, okay, so this is the first thing this problem I want to ask to do. Then the second one is here. So we say, okay, now I know instead of find the 5, I can just find the ones, right? So I can just find the ones here. Okay, so now the next things here, we say you want to find RU cross RV, so this will be a normal vector. But because this surface here, the green surface here, right? Because this green surface here is flat, right? So the normal vector really is just like this is my normal vectors here, right? So this is my normal vector. Is the RU cross RV. So, right, so this is the normal vectors here, right? So, correct? Okay, so that means I don't really need to go to find the RURV or the parameterization. So I can just say, hey, this one is really equal to what? The surface integrations, right? So then this is a curl F, and then I only need a what? What is this normal vector? It's the case, right? So this is the z parallel to the z x-axis. So I only need to cross, it's a dot product k. So that means it's 0, 0, 1, right? I only need to dot products that. So now we simplify that. Okay, so now let me put these ones here. So what is these things become to? So this is the curl f dot k. So really is equal to, I already find the curl of f is x squared z. This is xy minus 2xyz. And this is y minus xz. Then I dot product 0, 0, 1. Correct? Okay, so when you dot the product 0, 0, 1, so what is this one here? Is y minus what? Y minus xz here, right? Okay, so now this one's here, I finally can do, this is S2s, right? So this is a curl of the F for the ds. It's really, I'm just integrating what? I'm integrating y. Okay, so y and this one's here, right? Because this is the planes, right? So what is my z value on this green planes here? The z is equal to the -1. So the dot product will become what? Which will be 1 plus what? 1 plus x. So take a look. So now my integration is 1 plus x. Wow, that's really simplified, right? So this is dx dy. So what is the dx dy? Because it is from the vertices here. So this is -1, 1, -1, 1. So cool. And then when you try to integrate that out, in fact, this will give you zeros here. So this is a super, super good problems here. So what is the good problems for this ones here? So it teaches you several things. The first, we want to find the curl of the F. Instead of find the phi surface integration, then you use the Stokes theorem. They say, hey, I can find just the one, the bottom one, the green ones here, right? So the green ones here, I can just use one surface here. Then the next thing is they tell you, say, hey, instead of, okay, so instead of go to find the parameterization functions for the RU, RV, then because I know the RU cross RV is a normal vector, so because this plane is flat and parallel to the YZ XY plane, so that's why the normal vector is go this direction. So it's X is Z's, right? So that is another very key things here we need to know here, right? So that's why I said this problem is a super, super good problem here. Teach us a few concepts, right? And how do we put them together? So that's it's pretty cool. Okay, so the last problem I want to do is the problem number 9 here. So the problem number 9 here, so it said f of x yz, and it's the boundary of part of the paraboloid, right? Okay, so now I'm going to find the surface integrations for the curl f here, right? Okay, so let's take a look at the graph first. Okay, so this one's here, I think the graph is going to be something like that. It's something paraboloid, all right? So this is the, okay, all right. So now, first things here, use what, let's try to get the, so we want to find, right? So what do we want to find is, so what do we want to find is the curl. So we know the surface integration, the line integration, the F to the dr will be equal to the surface integration, and the surface is this surface is here, right? It's on the first octants here, right? Okay. So this surface, and the curve is what? The curve is this curve, right? So it's this curve here. All right. So now in here, let's say here, so this is the surface here. Then I want to find the curl F, right? The ds here. Okay. So, okay, so first things here, let's try to find the curl of the F here. Okay. So the curl of the F is equal to, so negative yi minus z, j, and minus x case here. All right. So the curl of F, where we use the same notation, the definition ijk's here, right? Then this is rho x, rho y, rho z's, right? Then you put this p is x, y, y, z, z, x, right? So then this will give you the curl of the F. And then we said, okay, this surface integration, I'm going to take the integration of the z is equal to 1 minus x squared minus y. Then you say, this formula is quite familiar, right? So because this is they give you a function. So based on my surface integrations here, then I immediately ring the bell, right? So then I can say, oh, this is my gxy function. So now I remember, right? So I recall here in the surface integrations here, right? So we said if you're in the surface integrations, and if f the ds here, if if your graph can be represented by z is equal to some functions, then we have this very, very handy formulas here, right? So this handy formula say will tell you this is what will be the rho P. Okay, then you say rho G, rho X, right? And minus Q, rho G, rho Y, then plus R, then the dAs here. Okay, so this is the general, this is the formulas we have in the sections. I think it's you know, when we talk about the service integrations here. All right, so now be careful here. Now I'm going to find the curls, right? I'm going to, so what we are trying to do here, we are trying to do, this is the curl. So let's basically, you need to use the curls here. So that means this, you need to replace this ones here with the curls, right? Okay, so now let's take a look. How do we write it out? And you will be surprised how simple, you know. So let's see here. This is the surface integration curl f ds here. All right, so then I want to apply to these formulas here, right? So this will be D, okay? Now let's take a look here. So you tell you rho negative P, remember it's a curl. So where is my negative P here? This is my negative P, right? So this is the PQR, right? Okay, so negative P, so it's a negative Y. Rho G, rho X, rho G, rho X, you take the partial for X is what? Negative 2X here, right? Okay, then minus Q. So where is my Q here? Is here, right? So this is my Q because I'm doing the curl F integrations here. So this is my Q, so minus negative Z, correct? Then the rho G, rho Y. So what is rho G, rho Y? It's negative 2Y, correct? All right. Then what is my R function? This is my R functions, right? So it's a negative X here. So I have a negative X, okay? So this is what? dAs here. Whoa, that's pretty good. I changed it to the X, Y, and the Z's here, right? Okay, so now let's try to change that. Okay, so now this one's here, this will be equal to, so you do so you simplify that, it's a positive 2xy, right? So it's minus minus, so this is 2xy. Then plus z, and so here, minus minus, so it's a negative 2y, okay? Still is negative, all right? Okay, so this will be the negative 2y times z, right? So what is z here? So z is 1 minus x squared and what? Y squared, right? So it's 1 minus x squared and the y squared here. And then, okay, then the last thing here is minus x, right? So it's a minus x and the dAs here, okay? Now I need to know the boundary of the x and the y's, right? So because this is a circle, right? So the region here is a circle. The boundary probably will be pretty messy. So every time you see here, what you're going to do? So you say, I need to change it to what here? You change it to polar, right? Okay, so now I can do the same thing. I can say x equal to the r cosine theta, y equal to the r sine theta. We are already very familiar, so Jacobian is r, right? Okay, so now I can simplify this ones here. Okay, so negative 2, so this is negative 2, r cosine theta, r sine theta, correct? Then minus 2 r sine theta. 1 minus x squared minus y squared is what? It's 1 minus r squared, right? then minus x minus r cosine theta, right? So this is the whole thing. And don't forget the Jacobians, right? And the dr d theta. Okay, now we simplify to all the r and the theta. So r is from 0 to 1. Where is the theta? It's 0 to what? Pi over 2. See here, right? Be careful, it's a pi over 2. Why? It's because I'm only on the first what? First quadrants, right? So it's a pi over 2. See here. So now if you calculate that and put it into the some integration software or you integrate it yourself, and you will get it. This is negative 17 to 20 here. Okay, so this is also is kind of like a very good problem to combine the knowledge from the previous things we learned, right? So of course, we need to know how to find the curl. Then remember, see here, when you do the surface integration, if your function z can be right, if the surface can be right as z equal to some function xy, and then you can use this very handy formula. Then the last thing is here, after you do that, because xy, they are in the circle things, so that's why, it's not easy to change the boundary with using the xy. So as soon as we see that, we say, hey, let's use the polar. So we change it to the polar. And so that's how do we integrate that. Okay, that's it. So I hope the 4 problems we practice here can help you to finish the remaining homework assignments. All right, that's it. Have a good day and enjoy to use the Stokes theorems. Okay, bye.